Thank you for joining. Today I want to talk about reactive programming from scratch. So my name is Thomas. I work at High Street here in Utrecht. We make shopping apps, mostly for fashion, and we try to make them really nice. And one of the ways we try to make them really nice is using reactive programming. And we use RX Swift and RX Java, so both on the iOS and the Android side we use reactive programming. RX, or reactive extensions, is one of the implementations of reactive programming. It was created at Microsoft, and right now there are many ports exist. So there's RX Swift, RX Java, RX JS, RX Scala, RX Kotlin, etc. So the good thing about using RX on both platforms is that the function names are the same, the concepts are the same. So in this talk I'll also be using the names from RX, which are a bit different from maybe Reactive Cocoa or Reactive Swift, but the concepts are the same. So over the next 20-something minutes, I'd like to build a minimal reactive programming implementation. That implementation should cover all the most important core concepts, and it should help build a mental model of what reactive programming is. So when you pick a real implementation, for example RX Swift, then you can apply that mental model and understand how you can apply that real implementation to your own real-world projects. So what excites me about reactive programming is that it's one solution that can help solve a wide variety of problems that we encounter in modern day app development. Whereas with imperative programming, you might have to switch between different approaches depending on the problem. But there's also a downside. Reactive programming can be a bit hard to get into. There is a learning curve, and it really requires a different way of thinking, a different perspective on things. So I'd like to start with a little exercise on perspective. Right here you see two pictures of the same event. It's the finish of a 2016 Olympics race. On the left you see a regular photo, and on the right, which might appear like a regular photo as well, you see a photo finish photo. And those things are fundamentally different. So I'm not sure if everybody knows what the photo finish camera does, but it actually takes a very, very small image, just 1 pixel wide, at a specific point in space, the finish line. It takes a lot of pictures and then stitches them together horizontally. I made an animation that does that. So it actually makes a lot of pictures, sees the runners going by, and then stitches together those pictures, and then you see this, see what the finish line looked like over the course of a fraction of a second. So a regular picture is a snapshot in time, and a photo finish photo is a snapshot in space. One thing that stands out is, for example, that the legs of some of the athletes are longer than others, and that kind of is determined by which leg they use to run over the finish line. So the leg that stayed longer on the finish line also looks longer on the picture. So how does that apply to programming? The regular photo is the case where we are working with our data in a synchronous way. We just have an array of data, have all our data, we can work with our data, manipulate it rather nicely. And then the second, the photo finish is the asynchronous case, where we're sitting on the edge of our seat and we're working with the data as it comes in, because we want to provide a nice and smooth and reactive app experience. So in this case we have this completion closure that gets invoked whenever an athlete crosses the finish line. And that's more or less how you could look at the photo finish camera. So these things are pretty similar. In both cases you're working with a sequence of athletes, a synchronous sequence or an asynchronous sequence. And you could write both cases like this, like the array literal syntax. Only for the asynchronous case you have to close your eyes, squint a little bit, and imagine that every comma is an undefined amount of time between those athletes. What I'm getting at is that everything is a sequence. Could be a synchronous sequence, asynchronous sequence, finite, infinite, or maybe even a sequence of one. But the good thing, if everything is a sequence, please allow me that assumption. If everything is a sequence, we only need one tool. And that tool, of course, is reactive programming. So if everything is a sequence, we only need one API to do great things with it. But what does that API look like? And instead of just telling you, I'd rather like to arrive at that API. And let's start by looking at a good first candidate, which is of course the standard library of Swift. So how does the API for sequences in Swift look like? You probably know that. So this is an example of a synchronous sequence. So get race results returns an array, we get the prefix, we enumerate over it, and we turn it in a string displaying the first 3 results of the race. Pretty nice. So now if we try to do the same thing for the asynchronous case, you don't really have to understand it, but just understand that it's a bit more difficult. You need another parameter to save temporary state, and in the end you can get this array of this string with the top 3 athletes, but it's not as nice. Because somehow these invocations of the closure are not iterable. You cannot work with them as if they are a sequence with Swift. So, but we can find asynchronous sequences in our work, in our code, but it didn't really change in Swift. We inherited those ways from Objective-C days, from the Objective-C days, from Cocoa libraries. So, for example, one example is a sequence of button taps. So we can use the target action pattern to receive the taps whenever a button is tapped, which is a sequence of button taps. Second example is the delegate pattern. For example, the collocation manager, where your delegate will receive coordinates whenever the user makes a significant location change. And then the third example is a sequence of 1, where you give a completion closure to the URL session, and you get the response of a URL request when it's done. So these are all sequences that we are going to be able to represent in Rx, but somehow it's not possible to represent them in the Swift library sequence API. And why is that? Well, I think at the core of the standard library is this possibility to iterate over the sequence. So you can do a for loop, for example. And this is all powered by 2 protocols mainly, the sequence protocol and the iterator protocol. So the only thing that the sequence, if you need to have a sequence, is have a method called makeIterator, and it should return an iterator. And that thing that is returned, the iterator, has to conform to iterator protocol. And the only thing that the iterator has is a function you can call next, and it will turn either the element, the next element, or nil when you're at the end of the sequence. And using just these two protocols, you can create really nice sequences. So let's have a look. For example, here we can make pretty easily a sequence, an infinite sequence that contains all natural numbers, so 0, 1, etc. I left the implementation blank for now, but it will fit on this slide. So you can instantiate it and then loop over it. And the only thing we need to implement, of course, is the makeIterator function. And in there we have to return an iterator. It's very easy to return any iterator, which just takes a closure that is called whenever next on the iterator is called. So in this case, we're going to be returning 0 for the first iteration, and then using the defer block, we'll increment the z every time, so it will be 0, 1, 2, etc. So we can loop over this with the for loop. And you might wonder, where is the iterator? Well, actually, this is syntactic sugar for something like this. So it creates an iterator and then calls the next function of that iterator. The one thing, of course, that's not so nice about this example is that it will never finish. You will run this, you can try to run it in a playground, it will never finish. It will just keep printing the next number. How come? But the Swift syntax is actually Swift sequence possibilities are actually pretty advanced, in that you could even work with these infinite sequences. For example, we could take a prefix of the sequence, just take the first 10 numbers, and it will work. It will print the 10 numbers and then continue on. You could also do other things. You could map over it. You have to use a lazy map though, because if you don't use a lazy map, it will first try to map over the whole infinite sequence, which doesn't work. But what about the asynchronous case? So this is all synchronous, right? But what if I want to do something like this, which makes no sense, but for tap in button taps, add the product to the cart. So I have a button on a detail view of the product where I can add it to the cart. And then whenever the button is tapped, for every tap, I want to add it to the cart. So this makes sense. If we speak this out loud, it makes sense, but somehow it's not as easy as this. Well, our X will get close. We could try to do it in Swift by having an iterator and then having a semaphore and pausing whenever we don't have the next step available and block the calling thread for the for loop. That really doesn't make any sense. So because the problem with the Swift sequence API is that it's really made for synchronous usage. And the for loop, the consumer determines the timing in which you want to get and receive the elements. So, and there's no way for the iterator, whenever next is called, to tell, okay, wait a minute, I'll get back to you when I have a new value. No, you have to either return it or tell that the sequence is over. So, to get very close to reactive programming, we just need to reverse this API, and then we'll see that we can actually cover the asynchronous case. So if we reverse the iterator, we end up with something that we could call an observer, not observable, observer. And it's actually the inverse, right? So where the iterator has a function returning an element, the observer actually has a function that receives an element. We can make a very simple implementation, just like a type-erased wrapper, where the initializer receives the closure that will get called whenever next is called. So this is the simplest observer that you can implement. So, extended library has an iterator and a sequence. We have an observer. So what's the fourth one? It has to be like the equivalent, but inverse API of the sequence. And this is called an observable. So an observable is something you can observe. It will be a sequence of synchronous or asynchronous data. And that protocol looks something like this. So instead of the sequence protocol that has a method make iterator returns an iterator, we can now pass the equivalent of the iterator, the observer, to the observable. So it's called subscribe. So you pass the operator, the observer, to the observable, and then they have to match types, of course. So you can have an observable with ints, and you also have to have an observer for ints. Again, we can have a very simple implementation where we can pass the implementation of subscribe to the initializer of the observable, and we can have a helper method that allows us to just pass the observer's next method, and we'll wrap it inside this implementation, inside any observer, which saves some typing. Okay, so what have we arrived at? We can now define an observable int, for example. We have to define it. When we define it, we have to pass it the closure that will get called for every subscription. So whenever an observer subscribes, this closure will get called. So what can we do inside of here? What we could do is do something with the observer. The only thing we can do with the observer is call next on it. So let's try that. So we could call next 3 times. This is basically a representation of a simple sequence 1, 2, 3 in reactive programming. For longer sequences, this becomes rather tedious, won't fit on the screen. So we could also create a helper function called from. We define it on observable. So we can do observable.from, pass an array, and that will turn that array into an observable. So what you see here is that we return an observable that for every observer will iterate over the array and call next on that observer for every element. When we use it, it looks something like this. So now we have an observable O that contains 1, 2, and 3. And we can subscribe to it and print, and it will actually print 1, 2, and 3. So that's pretty cool already. Might look like a lot of work, maybe. And before we continue, it might be good to really understand what's going on. And we're going to need the help of an emoji to help us. Because what we can do is we can give our observer a name. Let's call it cat. And we can follow along what the cat is, where it is going as it subscribes and as it receives values. So we define the observer cat, subscribe it to the observable. So it arrives in the subscribe method. It's then wrapped in an any observer, but that's just a done wrapper, so that's more that. And then the subscribe closure is called with, and cat is passed to the subscribe closure. So what's this subscribe closure? That's actually the closure that's passed on the creation of the observable over there. So, and how is the observable created? It was created from an array, right? So we created this array using this observable using observable.from, passed 1, 2, 3. So actually what we're passing is this closure that whenever an observer, when it's called for every observer, and every observer will receive every element of that array. So that's called 1, 2, 3, 4. So that's passed to the initializer of observable. It's stored in underscore subscribe. And that is actually what will receive the cat observer. So it will arrive here. And for each element in the array, cat.next will get called. And that's how, in the end, 1, 2, and 3 will be printed. And it fits basically in one slide. So it's not that much code, but on the other hand, you might think, well, this is more or less what you can do right now with for each. Yes, it's even a bit more verbose what we have to use. This is pretty much similar. The only thing, what's nice about the RX approach is that it will scale to the asynchronous case. So we can look at an asynchronous sequence. For example, this timer. Timer, you can say that the timer is an asynchronous sequence of 1. So we define a static function called timer. You pass it an int, number of seconds, and the returned observable will call async after on the dispatch queue for every observer and wait for the specified number of seconds, and then just emit one void element on the observable. So this is a 3-line egg cooker. You can ship it. So now, what would happen? This is a question to the audience. What would happen if we do this? So we actually use 2 timers. One at the top, and then inside a dispatch queue, after 10 seconds, we use the timer again. So 2 times 6 minutes. What do you think? What's the timing between those 2 print statements? Anybody? 10 seconds, yes. That's to warm up, right? So what happens now if we create this timer, write it to a constant, and then call subscribe twice on the same observable, and again the second subscription is made inside this 10-second delay.
They both fire at the same time?
No. That was the answer that I was hoping for, but it's not correct now, because actually no code we've seen so far, these 20 lines of code that we've written, share any state together. So there's no shared state. When you subscribe, the closure passed to the observable on the initialization is called again. So it's just a second timer that starts, in this case, 10 seconds after the first time. Every subscription is isolated. But that's not a very useful sequence. A more useful sequence is, for example, a network request, because a network request, you could say, is also an asynchronous sequence of 1. So in this case, we're defining a method called fetch, and it will return an observable that for every observer that subscribes, it will start a data task on the URL session for the given URL, and then when it's done, using the completion handler, it will emit the data and the response to the observer. So we can use it like this. We can call fetch for a certain URL, and then subscribe to it and get the data and the response. So far we've seen how we can create observables and observers and subscribe. Now let's look at one of the really cool things about RX, where but we can use operators to compose increasingly complicated and sophisticated observables together. So that started with a very simple operator. It's called same. So we define it on observable. You can call it an observable, and you just get a new observable that does exactly the same as the previous, the original observable. So same returns an observable that for every observer subscribes to the original observable, that's self, and just passes the observer along. We could also write it like this. So we actually define a new closure. That's the observer that will go to the original observable. And then whenever an element is received, we pass it to the observer. Not very useful. We can make it a bit more useful by defining an operator called +1 on an observable with ints, and we'll just add 1 to every element that is passed along. And this is already getting very close to something you all will probably recognize, and that's map. Like on array, map will return a new observable that contains all elements from the original observable, but then mapped or transformed through the given closure. So here you see that it returns an observable of a new type, U, which is also the return type of the closure that you have. And for every observer, it will subscribe to the original observable, and whenever it receives an element, it will transform it using the closure and pass it to the outer observable. And you can use it like this. So you can define an observable 1, 2, 3, and then map it through a closure that does some modulo operation, and then print. And it will probably print something like false, true, false. Let's have a look at how that works. Here's all the code involved. So when we add our cat observer to the when we subscribe to the observable returned from map, it will arrive inside map, and it will be kept there because it should get called for each element whenever the original observable emits an item. We can give the observer that map makes on the original observable, we can give it a name, let's call it a dog, and that arrives in our from method. So, and then here we iterate over this array 1, 2, 3. So that 1, 2, 3 is given to the dog. The dog will call f for every element, and will pass along the results of that f call to the cat. And what's important to realize when you have these impressive looking observables with multiple operators is that before you subscribe, actually nothing is happening. This O and this O1 are just a definition of your data flow. There's actually nothing flowing yet. But as soon as you subscribe, then the first items 1, 2, 3 are emitted. +1 will add 1. Map will turn it into a Boolean. But so everything happens in response to a subscription. That also means that if you subscribe twice, everything will happen twice. And in this case, with these simple operations, it's not a big problem. But what if you're doing network requests? So here I do a network request and subscribe twice. That's not really a good marketing slogan for a library, right? It's never been easier to make duplicate network requests. But good thing is that it's also quite easy. It's never been easier to share side effects like networking requests. So how do we do that? We can do that, of course, with an operator. So we can define a share operator. Again, it will fit on the slide. What we need to do is, so whenever we're going to return a new observable that should, no matter how many observers subscribe to it, only subscribe once to the original observable. So whenever an observer arrives, we're going to check whether it's the first observer or not, using this Boolean. And if it's the first observer, if we have not subscribed yet, we will subscribe to the original observable, the network request, for example. And then, of course, we need to store the observer in an array. We store every observer, not just the first, but also the second, third, and fourth. Because whenever an element is received, we need to send it to all interested observers. So if we use the share operator like this, so we fetch and then add the share operator to the end, Now actually there's just one network request going out. And it happens something like this. We have two subscribers, the cat and the dog. The cat first arrives in the share operator. It's the first one. So the subscription to the original observable is made. It's stored in the observers array over here. So whenever an element is called, is emitted from the original observable, it will be for each and will receive next. So this will also trigger, let's call it fish. That's the observer on the original observable that will arrive in the network request at the top. So and whenever the network request task is done, fish will receive next, and that means that this closure is called. But before that happens, luckily dog arrives, and it's added to the observers here as well. So now when the network request is done, in here, fish will receive the data and response that will end up here. So E will be the data and response, and both cat and dog will then receive the data and the response. You do have to note that share, the observable return from share has to be stored, otherwise it won't work, because we're actually defining the state and the scope of the whole observable. So if we would do this, see the difference? This case doesn't do anything. You're just sharing with on your own, which is not sharing at all. So this, if you want to do this sharing in imperative programming, you're already going to need another property that has some temporary value somewhere, or an array of completion closures, and you don't need that with Rx because it's all contained. The second example of containing state inside an observable is this very useful one, distinct until changed. I use it a lot to prevent the UI from updating whenever there is a change, but the change is just the same value as the previous value. So in here what we just do, we return a new observable that keeps track of the previously emitted value. If it's the same, if it's not the same, then we emit it to the returned observable. So we can use it like this. We can have an observable that contains 1, 1, 2, 3, etc. We call distinct until change, and then actually our subscriber will receive 1, 2, 3, 2, 3, 4. So it deduplicates subsequent identical elements. Very useful. And in here, it doesn't actually matter whether you use it like this and store the observable, or use it like this, because the state, keeping track of the previously emitted element, is contained to that single subscription. You can see it here more clearly if you compare share and distinct until change. In share, the shared state is defined outside of the return, so in the share level, and in here, it's, for distinct until change, it's defined inside the closure that's called for that specific observable. Okay, so we've seen observables, observers, subscriptions, operators, and sharing. So what about when you want to stop observing, right? With just the regular Swift APIs, it would look something like this. You're running through it could look something like this at least. You're running through the sequence, and whenever you find the thing you're looking for, you break and you have it. In reactive programming, it could look something like this. Where you have an observable and you just want to take the first 3, or you want to take elements until you find the needle. So then these operators will define new observables that will end and ignore the elements from the original observable. But that requires that we receive elements. You can only at the point where you receive an element, you can decide to stop or not. And that works pretty well in a synchronous case, but if it's an asynchronous case, for example, network request, it can take 2 seconds, or maybe 40, before the response comes back. And between the time that you start the request and 40 seconds later, you might want to stop observing that network request. You might want to cancel it. Maybe if the user taps the back button, you really don't want to hear about that network request ever again. But right now, as it stands, it's a bit of a problem because this closure here, this observer, will be retained indirectly through share and the block operation underlying operation queue of URL session. Because as long as the network request is running, it needs access to the observer to tell it about the response. So what we need to do is something like this. Whenever we subscribe, we need to return a disposable thing that we can call whenever we don't want to subscribe anywhere, whenever we want to dispose of the subscription. And that can be a pretty easy type, just call it disposable, and it's a closure from nothing to nothing. We need to make a tiny change to the observable, where right now, whenever you subscribe, you get the observer, but you return nothing. And the same goes for this subscribe. We have to change that into that you return a disposable, because the disposable is actually what we want to receive when we subscribe, so we can call it to unsubscribe. So when it looked like this before, where you have an observable, we define it with a closure that receives the observer, so we can do some work. We now have to return a closure that whenever it's called, will cancel that work and dispose any side effects. So for the network request, this would look something like this, right? It looked like this, now it looks like this, where we return a closure that whenever it's called, we will cancel the task that we started. And on the call side, it looks like this. So we subscribe to the network request, to the observable return from fetch, and then maybe later when the user taps the back button, we want to dispose. In practice, we'll usually do something like this, where we have our view, and in our bind method, we bind our view model, we bind our title to a title label, but we don't want to keep updating the title label after our view is gone, so whenever we de-init, we call disposable, and the view model will stop updating the title. It's still very important to make sure that you only have weak references inside the observer, because otherwise view will never get dialogued, and then your de-init will never get called. Retain sound. So, and for operators, it's actually pretty minimal change. We just have to add a return statement, because this operator has no state of its own. So we just, but it might depend on an observable that has state on its own that needs disposing. Share is a bit more complicated. A little bit more room, because you can understand that whenever one of the observers disposes of the subscription, that observer should not receive any updates, but the other ones still should. And when the last observer disposes of the subscription, only then you want to dispose of the original subscription to the original observable. So what we're going to do, we're going to return this disposable. So whenever the observer, we keep track of the index where the observer is stored in the array of observers, and we nil it. And whenever it's the last one, we will also dispose of the original subscription that could, for example, be to a network request. So now we know how to stop observing. Last bit that I want to talk about is a specific use case where the source of elements from your observable is a bit different than just an array of elements. For example, button taps. So here we have a view controller with a submit button, and in view.load we want to bind our view model, we want to give it the observable containing the taps of our submit button. These taps are received here in the IB action method. But there's two things we want to do, but we can't. Either we want to get the tabs here inside this closure, so we can call observer.next, but how do we get tabs inside this closure? Or the other way around is that we would have the observers here, but we don't have them because they're here. But we can find a way to get them there. And what we can do is we can actually add property observers on the view controller that has all the observers. Whenever an observer subscribes to the tabs, we add it over there, and then whenever a button tab happens, we will invoke next on all registered observers. Actually pretty similar to the share operator. But this, of course, you don't want to have this stuff in the view controller, so we can get it out of there and just create a new kind of observable called button observable, where we have all the stuff about keeping track of the observers. And whenever tab is called on button observable, we call next. And then the view controller already looks a lot nicer. We just have to keep this button observable here, pass it to the view model, and whenever a button is tapped, we call tap on the button observable. We can make it a bit more generic to arrive at what actually is being used in RX. We can make this generic. So we can make it generic to the type. Not just tabs, not just voids, but anything. It can be ints, rules, name it. That means that the tab method needs to change. We need to give it an element. And this looks very much like a method that we've already seen earlier. But back then it was called next. Maybe let's just call it next. Like this. Let's call it next. And actually that makes this thing that we're making both an observable and an observer. So we can pass the next element to the button observable, and it will also arrive at all the subscribed observers. And this thing actually is called a subject in RX. So that's what we can use in our view controller. We can create a subject with voids, and whenever the button is tapped, we pass void. This is the way we pass void in Swift 4. We pass void, and then the view model will receive it. So that's subjects, a very common concept to use whenever you get elements from outside of your RX world, for example, UIKit, your button tabs. Okay, so tonight we've seen the observer, the observable operators, subscribing and disposing, sharing side effects, the subject, and all these concepts, I think, make up the core of reactive programming. But of course, there's a good reason why real reactive programming implementations are not 50 lines of code, but 5,000 or maybe 50,000, because I also ignored a lot. Our observables right now just emit elements, but it might be useful also to be able to emit errors or indicate whenever an observable completes. So usually real implementations emit an enum with next error and completed. Then there's of course a lot of work done about concurrency and thread safety, and a lot of optimizations and operators and operators and operators. So there's a few nice things to look up maybe if you want to look more into reactive programming. There's a really nice introduction by André Staltz in a GIST. There was also a nice talk at UIConf by Brandon and Lisa from Kickstarter, where they talk about how both iOS and Android teams use RX and how they can learn from each other and help each other. And of course, just check out these projects, RX Swift, Reactive Swift, ReactKit. They have great readmes, most of them, documentation, and just play around. Thank you.
Are there any questions?
Thanks for the talk. I had a question about subscribing to asynchronous events. You, for example, do the share so that multiple observers can subscribe to one.
Yeah.
I was wondering what happens when you have a stream of asynchronous events, and for example, or just a single one, and I'm interested for every new observer in the last one plus any next ones. Is there a thing for that?
Yeah, right. So you're alluding to replay behavior. It's very common that you want to not only share, but also remember the latest element and emit that to every new observer. Because in this case, I didn't tell you, sorry, this sharing with this network request, what will happen if you subscribe only after the network request is done, you won't receive anything. So you want to replay the last element, the response from the network request. So even if you're only subscribed after the network request is done, you still receive the data.
Okay. Thanks.
you store the state for the shared and the other one in the function. So I was wondering where is that value retained? Because normally in the function the value is gone when you reach the end of the function.
It's retained inside the closure that's passed to the returned observable. So you create an observable with the subscribe closure that you pass the initializer, and it will retain actually by reference those state variables. But in real implementations, you probably would have a subclass of observable instead of just returning them inline like I did. But that will make it 10 times more code.
I don't know if you've seen have you seen the proposal for async await and coroutines in Swift? Hopefully Swift 5.
Yeah.
How do you think that's going to impact the RX world for Swift?
I think async await will do wonders for futures and promises. I think it's going to be awesome. But I don't think it will apply or do really anything for the reactive world, because for reactive you really need streams of values, and async await is really for just one asynchronous value, as I understand.
Yeah, no, that's correct. I mean, in a way, that's how a lot of people use reactive as well, right? So say you orchestrate calls and that kind of stuff that now will have coroutines and that it's going to get a lot better.
Right, so whenever you use observables for an asynchronous sequence of one, so just one element, then async await might be nicer. And I can imagine that they make ways to easily turn an observable into an async await and the other way around. Then we have to wait till Swift 5.
Yeah.
So you've shown us the share operator, and once you use the share operator, then you have to hold on to that observable to let other people subscribe to it.
Yes.
But one thing I think is hard with RX is that it isn't visible that is an observable that is shared, for example. So there's no way, the type isn't changed, there's no indication that is a shared observable. And also you've now talked about observables that only start to do things when you subscribe to them.
Yeah.
But you also have the kind of observables that are called hot observables, that are doing things already, and you subscribe to them, and then you just get what they're then doing at that moment.
Yeah.
And that's also a thing that you can't see if you get the observable back from a function, for example.
Yeah.
So in my experience, that makes RX kind of hard to use and kind of hard to grasp what is going on if you're coming into a new code base that maybe isn't that nice because you couldn't write it yourself, so you don't know anything about it. So what's your thought on that? Is RX then a tool for a specific job? Should you use it always or only in specific apps? Or is that a thing you don't think is really a problem? What's your thought on that?
Well, I think it is a problem in a way because you lose some expressiveness because whenever you return an observable from a function, you don't know if it's going to return nothing, one thing, 1,000 things, synchronously or asynchronously. And right now, I think the only way to do it is by documenting it, which is not as nice as having the type system solve it for you, right? Maybe in Java you can do something with annotations and make it clearer using that. I know RX Swift defined lots of traits, they call them, so specific the observables that behave in a specific way, like a driver, which will always emit values on the main thread and always repeat the last element that was whenever you subscribe. Variables, completion singles. So then, in a way, you can wrap this very generic, but also a bit vague observable in a type that makes some guarantees about its behavior. But that's definitely something you build as a layer on top of this. And I myself use mainly document the functions to describe what my observables will do.
Yeah, I found it quite interesting that the type layer you talk about, like singles and drivers, etc. That's a concept that's not available in every implementation.
Right.
It also differs a little bit between implementations.
Yeah. That's also why I like it less, because we can use it on the iOS side, but our Android people, whenever I write Android code, I cannot use it, so I'd rather maybe not use it and keep it the same. Thank you.
Do you have a recommendation on how to debug RX? And I think I have some ideas, but I also know the first time you put in a breakpoint and you open the backtrace, it really scares you away. So I thought maybe it's you can give some advice here.
Yeah, like with futures and promises, for example, debugging is hard, and with reactive programming, debugging may be a bit harder because you indeed get a lot of stack traces with few lines, your own code, and lots of library stack frames. There are a few solutions. The main one actually is a debug operator that will just print everything that happens, everything that passes along. So the debug operator returns a new observable that passes everything along and prints it. So that's nice. But that's a bit like debugging with print statements. Nobody does that, right? except if you're using Swift and LLVs. And there's also experimental work, but that's more, I think, in academia, where they have visualizers of streams. I think most of that is done in the JavaScript world, so if you're really stuck, you can port your JavaScript code to JavaScript. Yeah, it would be nice.
I do a lot of 2D programming. How does this relate to 2D? Does it make things easier or harder? Have you ever experience with that?
Yeah, I think it's very similar to asynchronous testing in general. So it might be that you have to like wait at the bottom of your test function until all asynchronous things have completed. But then, of course, you don't want to wait for a network request or like multi-second timeouts. So you can, with dependency injection, you can make sure that these timeouts don't happen or these delays don't happen while testing. You can also turn observables into blocking, so that will really block the thread until it receives an element. Might be nice to use, might be easy during testing, but not so nice in production. But all in all, I think it's if you use the default XC test, you can use the XC test expectation and resolve it inside your subscription, for example.
On TDD, I've worked with RX on a project where we had a requirement like if something happens again within 5 minutes, then we should do something. But if it's after 5 minutes, we shouldn't do it. And that's amazing with RX. Because you have virtual time. So in a test, you can say, we emit this value at 0 seconds, then again we emit this value at 30 seconds, and then we check if the expectation happens. And that runs just in like a zeroth of a second, because it isn't real time, so it isn't waiting for the 5 minutes to happen, but it's just running at once. And that's I think one thing of RX that's like amazing that you haven't, that you can't do with any other library. That's quite interesting.
Yeah, I haven't really touched on anything about switching threads while you're observing that. You could do a map on one thread and then the next operator on another, and you can inject like fake schedulers while testing, so they are not really waiting 5 seconds, but doing it immediately, for example. Yeah, thanks.
Yeah, that's quite amazing.
Yeah.
Thanks for the talk. I want to ask about Dispose and the subscriptions.
Yeah.
You explicitly unsubscribed in the init method, and it's like mixing imperative and declarative styles. It's a common practice in RX, or it's just for simplicity?
Not. This is more or less how you do it. You can hide it a little bit more, but you have to tie it to the lifecycle of your context, your view, for example, and that is imperative because that's the framework that Apple gives us.
Yeah, no. For example, in Reactive Cocoa, you have take until something, and you can pass as a observer, and it will kill as a subscription. So it's more like declarative in all the way.
Right, but then you pass an observer, so that take until will take another observable, and whenever that one emits, then you unsubscribe from the original observable, right? But then who emits on that observable that you pass to take until?
Take until dialog.
Yeah, so there, hidden somewhere, is a dialog block.
Yes.
So it's still, so you can hide it, definitely, and make it more declarative.
but there is some imperative thing that you have to receive from UI thing, which is imperative. You can hide it more. Yeah. Thanks.
Okay. Thank you very much.